Greetings, detectives. Mrs. McKay here, and it's time to work on Clue 3, Factors of Change. And this is in Case 4, which is called Growth Pattern Change-Up. And our Clue 3 is very similar to Clue 2. It says, I can identify the change factor Let's go ahead and write this in. The change factor in an exponential function as equal factors over equal intervals. Now, if you can remember, in linear functions, we had a rate of change, and that was often represented by slope. And it was equal differences over equal intervals. So as x changed in an interval, usually by 1, but could have been more than 1, there was a difference that was added to from each y. You could look at it and you could see that y changed. There was a difference. And so now, and it was just you either added or subtracted it, right? So now we're going to be talking about, as our intervals change in the x, our y values are going to increase by factors, meaning we're going to be multiplying by something, all right? So before we go any further, it's very important to talk about some of this vocabulary. The first thing is the word exponent, and everyone needs to understand what an exponent is. An exponent, if I have 3 to the second power, the exponent is that little 2. This is the exponent, all right? And that is a power, which means that I'm going to multiply the base, which is the bottom number, by itself that many times, okay? So I'm going to take 3 and I'm going to multiply it by itself 2 times. So that would be 3 times 3, all right? So it's important that you know that, and it's also important that you're comfortable with negative exponents. So let me just show you what I mean by that. If I say 3 to the negative 2 power, what does that mean? Well, that really means 1 over 3 to the second power. Okay, remember that negative exponent does not mean that this becomes a negative number. It actually becomes a fraction. And if you remember my little saying, cross the line, if you think of this as 1, cross the line, change the sign. So we move the 3 down below the fraction line. There's a 1 that remains, and the sign of the exponent changes to positive. So negative exponents are really multiplying by fractions. So 3 to the negative 1 is really equal to 1 over 3. Okay? And the last thing is a constant ratio. And we used constant ratios in arithmetic sequences. So when I had an arithmetic sequence like 4, 8, 16, 32, we saw that our constant ratio was to multiply by 2, because each time we multiplied the previous term by 2, and that's called a constant ratio. And a constant ratio is very much like a change factor, okay? Just like in I think I said in arithmetic sequences. I meant geometric sequences. If I said arithmetic, I meant geometric. So in arithmetic sequences, we had a constant difference. And that was a linear function. And in geometric sequences, we have a constant ratio, and that is an exponential function, which is what we're going to be talking about today, exponential functions. All right? The difference between arithmetic and linear is that an arithmetic sequence is a type of linear function. In the same way, a geometric sequence is a type of exponential function. Sequences are discrete, meaning they're individual points, whereas functions can either be discrete or continuous. And so what we're going to be talking about more now are different types of exponential functions that are not discrete but continuous. All right? So now let's go ahead and talk a little bit about some of the characteristics of an exponential function. The first thing that you'll want to know about an exponential function is there are two variables. There's an x and there's a y. Or you might see it like this, an x and an f of x. Same thing, the function of x, all right? So the other thing is that we still graph it on a coordinate plane. But so remember, f of x is the same as y. It just means the value of x when we apply the rule. All right, so that's similar to linear functions. The main difference about an exponential function is that the variable x is always an exponent. Let me show you what I mean. Y equals 2 to the x power, or f of x equals 3 to the x power. The x is the variable. I mean, obviously we know that. The x is the exponent. You might even see it like this. X, let's see, f of x equals f of x equals 4 to the x minus 1 power, which is what we saw in geometric sequences. But either way, the x is always the exponent. Do you see that? Every single time it's the exponent. It could even be this, y equals 5 to the negative x. Okay? You can even have a negative, but the x is always an exponent. All right? The next thing that is a characteristic of an exponential function that's very different from a linear function. Remember, a linear function, when you graph it, is a straight line. Okay? It's a line. But in an exponential function, you're looking at a curve. Well, see if we can fix that. Here's my x and my y. And an exponential function starts off growing very slowly. Okay, it'll start off, and it can start really anywhere, but often it starts in front of the 0, okay? But it could be down, it could be over in the negatives, it could be below, it could be in lots of places. But it's going to start off very slowly, and then it's going to shoot up almost straight up, okay? So an exponential function starts off, grows very slowly, and then suddenly it rapidly increases and shoots straight up. Kind of explodes, okay? This is called exponential growth, all right? Exponential growth. But there's another kind. It's called exponential decay. And that starts off at the top, starts off here, and comes down like this and approaches 0 like that. And that's called exponential decay. All right? So growth and decay, but both of them have this sharp increase or decrease and a very slow slow increase to a sharp increase, or sharp decrease to a slow decrease. All right? So the thing that's important is to learn how to recognize these curves. All right? You want to be able to recognize those graphs. Now, an exponential function, what we will know are two different forms. One is the standard form, which basically says f of x, let's use y. We'll use y just to make things simpler. F of x or y both work, all right? But we'll say y equals a to the x power. And a is a constant, okay? A is the constant. You want to remember that. A is a constant, okay? So it's some constant to the x power. And we've already learned the recursive formula that basically says f of n equals whatever the first term is, all right? And, I'm sorry, we want to say this is f of 1, not f of n. We want to say f of 1, we always say what the first term is. F of 1. And f of n is equal to f of n minus 1, which is the value of the previous term, times the constant ratio, okay? Times the constant ratio. So we already learned that one as well. So we have two constants. It's the first term and the constant ratio, and that's a recursive form. All right, so the last thing that I want to talk to you about with exponential functions is that they have a constant rate of change, but this time it's not a constant difference, it's a change factor. So we actually are not going to call it a constant rate of change. We're going to say it has a constant change factor. All right, and I'm going to show you what I mean by that. Let's imagine that I have a table. We'll say x and y. And this is that constant, that equal factors over equal intervals. So let's say we'll just have our equal intervals be 1, 2, 3, 4. So x is increasing by 1, all right? And our y is going to be 2, 4, 16. Oops, sorry, not 16. That would not be correct. 2, 4, 8. Let's make that be an 8 and a 16. Okay? 2, 4, 8, 16. So what we're looking for is we're looking for a constant change factor. That means what are we multiplying 2 by to get to 4? Well, we're multiplying by 2. And what do we multiply 4 by to get 8? Well, we multiply by 2. And what do we multiply 8 by to get 16? We multiply by 2. And if we were going to graph this little line, or this function, we would say, here's 1, 2, here's 2, 4, and 3, 8, and you can see how it's going up higher and higher and higher, right? So this is an exponential function. Now, you might also see it looking like this. Your change factor might be a fraction. Let's start with x and y. Let's say this is 1, 2, 3, 4. And we'll say that this is 27, 9, 3, and 1/3. Okay? So what did we do to get from 27 to 9? Well, you might say, well, we divided by 3. That just means that we multiplied by 1/3. So that's our change factor. Okay? And from 9 to 3, we multiplied by 1/3. And from 3, actually that should be a 1. We multiplied by 1/3. And then the next one, the 5, would have been a 1/3. Okay? So a constant rate of change means that we're multiplying by the same thing to get from each y value to the next y value. All right? And that ends up being our constant right there. Okay? Our A is what we're actually doing. So we'll look at that a little bit more closely later. Now or in another lesson. Let's go ahead, because really all I want you to do is recognize that these are equal factors over equal intervals. All right? So let's take a look at this little example here. The change in the height of the ball from one bounce to the next if the ball is dropped from a height of 8 feet and the ball bounces to 80% of its previous height with each bounce. So how would we look to see what the factor of change on this is? Let me show you what I'm doing here. So here's the number of bounces. Okay, that's the number of bounces, and this is the height. So at 0 bounces, before we bounce it, okay, how high is the ball? It's 8 feet. All right? After the first bounce, it goes down. So here's the ball. It goes down, it bounces up, but it doesn't go all the way. It only goes 80%. 80% of the 8 feet. So what's 80% of 8? Well, let me pull out my calculator quickly and do 8 times 0.8. And that's 6.4. So I'm going to write here 6.4. And what did we do? We multiplied by 0.8 because that's 80%. Okay? On the second bounce, the ball came down and it only went 80% of 6.4. So that's bounce 2, and we need to know what 80% of 6.4 is. So I'm going to take 6.4 and times by 0.8. And I get 5.12. Again, from 6.4 to 5.12, we multiplied by 0.8. And on the third bounce, we came down and only went up 80%. So we need to figure out 5.12 times 80%, and I get 4.096. So each time, my number's getting smaller. So if I was actually going to graph this, see if I can graph it. Let's see, at 0, we'll have this be 8 right there. So at 0, we are at 8. I should use a different color. At 0, we are at 8. At 1, we are at 6.4. We'll say it's right about there. At 2, we are at 5.12, and at 3, we are at 4.6. So you can see that this is going to kind of come down very slowly. It's going to look something like that. Okay? It's not a line, it's actually a curve. It's just not a very good curve. Okay? So if I was going to write this, I would say that I'm going to take whatever y is, it's going to be, b is going to be my x and y is my height, okay? Whatever, I'm going to take y equals, and I'm going to start with 8, okay? And I'm multiplying it by 0.8 to the x power, all right? So I always have to have my starting point, but my 0.8 is my change factor, okay? My 0.8 is my change factor. It's what I'm multiplying. It's what I'm multiplying by itself. Notice here, each time I multiplied by 0.8. So to get to term 2, to get to the second bounce, I took 8 and I multiplied it times 0.8 2 times, right? Times 0.8 2 times, 1 time, 2 times to get to 5.12. So my 0.8 is my change factor, and the exponent is the number of times I multiply it by itself. And the 8 is just where I started, okay? So that's just a quick little explanation of exponential functions. And the key for you to probably remember the most is that the variable x is the exponent and what the graphs look like. All right, those are two really important things. So now let's go ahead and do some examples. Take a look over here at y equals 3x plus 4 and tell me, is this an exponential function? And if it is, what is the factor of change? Now, so hopefully you noticed that this first one, y equals 3x plus 4, is a linear function. It's in standard it's in the y equals mx plus b format, slope-intercept form. This is not an exponential function, okay? It's not an exponential function, so therefore there is no change factor, okay? There's a rate of change, which is 3 over 1, but there is no change factor. We're not multiplying the, we don't have this exponential multiplication thing going on. All right, let's look at the next one. F of x equals 2 to the x power. Is that an exponential function? And if so, what is the change factor? All right. Well, hopefully you noticed that immediately that there was the x, the variable, was an exponent. So yes, it is an exponential function, and the change factor is 2 or times 2. Okay? We're going to multiply by 2 over and over and over again. Remember, I told you that this base ends up being our change factor. Let's look at the next one. Y equals 3x squared plus 4. What do you think? Well, you saw that there's an exponent in this one, right? But is the exponent a variable? No. The variable is the base, and therefore this is not an exponential function. It's actually called a quadratic function, which you'll learn about either at the end of this year or the beginning of next year. Quadratic functions are different. Quadratic functions actually look like U's or upside down U's. And remember, an exponential function is a steep incline like that. All right? So no, that is not an exponential function. Next one. F of 1 equals 4, and f of n equals f of n minus 1 times 3. Is this an exponential function? If so, what is the change factor? Well, if you are remembering your arithmetic sequences, you'll see that this is a recursive formula where we basically say that here's where we start. We start at 4, okay? And we are going to find the next term by looking at the previous term and multiplying by 3. So, yes, arithmetic sequences are exponential functions, and the change factor is right there. What do we multiply each term by? We multiply by 3. All right? Next one. 3, 9, 27, 81. Another, I keep calling these arithmetic. This is a geometric. Ignore me when I say arithmetic. I mean geometric. Geometric sequence. Take a look at this one. 3, 9, 27, 81. This is a sequence. And decide if it is arithmetic or geometric. And if it is geometric, then it should be an exponential function. And if it's an exponential function, it should have a change factor. So tell me what it is. So you should have noticed that each time you multiplied by 3, which means this is a geometric. It's a geometric sequence, and therefore it is an exponential function, and the change factor is times 3. Okay? So, last one. Here are days and how many bacteria are in a population. So on day 1, there are 10 bacteria. On day 2, there are 100 bacteria. On day 3, there are 1,000 bacteria. On day 4, there are 10,000 bacteria. Is this an exponential function? And if so, what is the change factor? Well, this one, you should have noticed right away that to get from 10 to 100, I had to multiply by 10. And to get from 100 to 1,000, I had to multiply by 10. And to get from 1,000 to 10,000, I multiplied by 10. So I have a change factor of 10, and therefore it must be an exponential function. Well, that's exponentials in a nutshell, and I know that it feels like a brand new topic that you may not be comfortable with. Again, the thing to remember is what an equation looks like, what a graph looks like, and how to recognize it in a table as well. All right? So go ahead and write yourself a key idea, something that's a big idea that you want to help remember this. This is something that you could look at when you are studying for a test or when you're reviewing for cracking the case. Look at the big idea and it helps you to remember what's the one thing that's really important. So once you've written your key idea, then you're done, and I'll see you in class.